Thank you, Aparna. Thank you, Professor Tharamani, for the wonderful talk. And as you can see from the audience, the response has been quite enthusiastic and a lot of questions have come in. So without any delay, let me start with the Q&A session. The first question, Professor Tharamani, is from, I guess, from a young researcher or maybe a graduate student who is asking about what should be the ideal over potential value for HER and OER.
Ideal potential for HER and OER. So obviously, so if you go with that, so it is 1.23. So far it has been reported almost close to 1 volt in the case of ORR. And the same goes with the HER. This is a 0. So most of the time, obviously, people do claim that it's a 0 voltage, but still we do see almost 0.05 or 0.1 or whatever it is. Even if you are able to approach at 0.1 volt, this is a quite good in the case of HER. But obviously, ORR is flooding, so that the potential is most of them are reported more than 1 volt.
Yeah. All right.
But it is more than the onset potential. Off-wave potential is very important in the case of ORR. So although sometimes we do reach the ORR, the onset potential, but the off-wave potential is quite low.
Tharamani. So I'll once again take up one more generic question where the participant is asking about the field in general, green hydrogen production, and why is it not, like, what are the bottlenecks and challenges in the field kind of pace up with coal, petroleum, and other non-renewable sources of energy? Yeah.
The challenges, if you go in terms of challenges, obviously the storing of hydrogen is one of the challenges here. So therefore, we are going with the different, obviously, so that even we are producing the various technology by whatever the brown technique or the green technique or whatever the techniques we are trying to say that. So again, storage is a big problem. And also the challenge is again the catalyst. So far the state of art catalyst, although there are a lot of literature that claim that we are producing so and so, still the state of art catalyst remains as a platinum carbon. If you want to for the marketing and other things, it's quite expensive. So the storing is the biggest problem. So we have to find the solution for the storage. And again, the cost effectiveness of the process. And also we have to come up with the various alternative techniques rather than this one. So now one of the promising is the H2S. Obviously, one can work with the H2S, and again, we have to increase the efficiency and so on.
Yeah, all right. Thank you, Professor. So I'll come to the work-specific question for the work on COFES2 trifunctional catalyst. There's a participant who's asking, is there a universal electrolyte that can be used for all the three reactions, OER, ORR, and HER?
Okay. Universal, see, we use the terminology called the universal here only for the hydrogen production. Obviously, we have tested in the acidic media as well as the neutral media and also the alkaline media, any of I showed here. So because the hydrogen production, this can be utilized in the water alkali and the chloroalkali and also the water electrolyzer. With that aim only, so we checked only with respect to the hydrogen evolution reaction as a pH universal. Obviously, one can check because if it is in the neutral media, obviously it is very good because most of the time it's quite challenging in the case of the alkaline media and all. However, again, the kinetics is quite challenging in any media. One can go with they can use the terminology universal.
Yeah. All right. Thank you, Professor. So I'll pick up another question where the participant says sulfides are known to oxidize. So was there any specific experiment to rule out the fact that the current is only from water oxidation and not from sulfur oxidation?
Come again the question?
Sulfides are known to get oxidized. So
yes,
analysis to rule out the fact that the current we measure is from water oxidation.
Yes. So we have done the control experiment and also the post analysis to demonstrate even in the absence of H2S as well. And it was proven that the sulfides are not involving in this oxidation. Already have given the example with respect to the H2S, where we, without a catalyst, we have utilized and we shown that we did not see anything. And also in the absence of H2S, the similar kind of experiments we have done with the absence of the sulfide as well for the water splitting, and we did not see the participation of the sulfide catalyst in the water splitting or the oxidation of the sulfide here.
All right. Yeah. Thank you, Professor. So Again, another specific question is, during OER, will iron undergo oxidation from iron 2 to iron 3? If it gains iron 3 oxidation state, it is very difficult to reduce it to iron 2. How will it affect the stability and turnover frequency of the catalyst?
Yeah, actually, in this case, what we have done is that, so as I said, that this material has the intrinsic nitrogen and carbon. So especially this will help the interaction due to the interfacial coupling between the heteroatom and also the metal sulfide in this case. And here the active site is, I'm not going to claim this as only the iron here. So we are going to claim this as the iron and also the cobalt. Oxyhydrox are involving in this, both in the case of the oxygen evolution as well as the oxygen reduction reaction. Again, obviously, it goes with the multiple step here. And this, in the case of oxygen reduction reactions, the presence of nitrogen obviously promoting the or enhancing the electrocatalytic activity here. And so it is depending on the oxygen absorption again. So therefore, due to the presence of these two metals, so that we can enhance the electrocatalytic activity, and it won't be a problem here. Obviously, if you go with the individual as a iron catalyst, yes, it's quite challenging.
All right. Thank you, Professor. So the next question is it possible to reduce H2S into elemental sulfur without using rare earth metals or catalysts?
Yes, that is what we have demonstrated one with respect to. Obviously, any electrode material, let's say glassy carbon or the graphite electrode or the nickel foam, if you take it as a working electrode, you will produce a small amount of a polysulfide. As I said, our aim is not to directly produce the sulfur. If we produce the sulfur, it is immediately deposited on the electrode surface, and we cannot perform the experiment because it acts as an insulator here. So therefore, our aim is to produce, that means we are restricting the potential at the polysulfide, lower order polysulfide, that it goes into the solution. So without a catalyst as a substrate with respect to the glassy carbon and also the graphite, you can see that the yellow color in the solution, it I already shown, it produces, but the amount of sulfur polysulfide is quite low, and then you can extract it over there. So relatively, it is very low, but obviously one can produce it, but not directly the sulfur. Again, it has to go with the acid treatment or the auto oxidation.
Yeah. So, Professor Tharamani, I guess it is already time, but is it fine if you take up?
Yeah, for me, yeah, please, you can go ahead with all the question, not a problem for me.
Yeah, thank you, Professor Tharamani. So the next question is on the ACCM work, where the participant is asking, why is the glassy carbon electrode preferred for this type of electrochemical ACCM studies? Why not other electrodes like carbon paste electrode or metallic electrodes like graphite electrode?
Okay, now, so actually what we need, that we need a homogeneous surface. In the case of ACCM, you can see that. So because in the bulk electrochemistry, so we take the 10 ml, 25 ml or 50 ml or whatever the solution. But in this case, we are taking very small amount. It's about 0.5 ml or even less than that. So we have the glassy carbon, assuming the glassy carbon is homogeneous and it's a smooth surface, and we have to place the electrode, the electrochemical cell on top of it. So, and with the help of the O-ring. In case if the surface is rough, obviously one can go with the graphite electrode. And if you want to use the nickel foam, then again, obviously you have to design. One can customize the electrochemical cell. It is not a standard. So one can have to make a hole and you can place a electrode over there and then can. So there's no restriction of utilizing any electrode. Actually, the aim of this SASM technique is to develop the membrane electrode assembly. If you go with the membrane electrode assembly, so it's the surface is quite rough. Only thing is the designing of the cell is. In our case, we wanted to understand the local catalytic activity of our particular catalyst, and we wanted that there's no leakage of the solution, and we want to place the electrochemicals on that. So we have chosen the glassy carbon.
Okay, yeah, I guess that answers it. Another question, Professor Tharamani, is on the byproducts of H2S electrolysis. So what are the byproducts of H2S electrolysis, and what are the environmental implications of such byproducts, if any?
So far, we did not find any byproducts, and now with the various techniques, we are trying to analyze it because we are trying to change the pH of the system also with the neutral media and so on. At this moment, whatever we have done it in the alkaline media, we did not see any byproduct except the lower order polysulfide, which has been monitored through the UV visible also. And so through the polysulfide, so that we are extracting the sulfur here.
Yeah. Thank you. Professor Tharamani. So I'll ask the last question to you, and it is a very generic question. If you can share some closing remarks on the
Mhm.
scope of research in this field, and especially about how green hydrogen in India is shaping up.
Okay, so the future of this one, obviously, this is one of the promising technology and it's a booming area. One can go with that. So that, as I said again, so that although people are working extensively on the electrochemical water splitting, and now we are coming up with the self-powered. So because we want to reduce the overall cost, so therefore we are eliminating this one. In that case, the challenging task is that again, although the on-site potential people are climbing more than 1 volt, but as per the DOE, so it has been a 9.9 volt here as the offset potential. If you could able to reach with respect to that, so one set of experiment is over for the cell, this especially for the self power. At the same time, we have to aim at the development of the catalyst, also the stable catalyst for the production of the rate of hydrogen should be increased over there. And apart from this, obviously nowadays, so there, as I said, that ammonia is also one of the promising source for the hydrogen. People can aim at to go with the oxidation of that to produce the hydrogen as well. So this is one of the promising area. People have that. This is what I said, that HTS, not many people are aware about it. This is one of the open research area. One can go with that, and this is an industrially important one where you can convert the waste pollutant into the value-added product, not only the producing the hydrogen and also has a sulfur.
Yeah. Thank you so much, Professor Tharamani, for your time. There are still questions coming in. So if
yes,
you're,
I'm very happy to. Yes, please go ahead. Go ahead.
yeah, I guess in the interest of time, we'll close the session. But if you're fine with,
Yes, I'm fine. For me, I'm fine. So it is depending on you people.
okay, so I can take maybe the last question. So the last question is water electrolysis really energy efficient? Because it requires at least 37 units of electricity for 1 kg of hydrogen. So can we not use this electricity directly to the battery for transportation or in some other efficient way?
And that's the reason, so we are proposing the self-powered, so where we are introducing the zinc air batteries. So our aim is also to reduce the cost of this hydrogen. Yes, alternative one can go. Actually, this is the integrating the any energy storage devices to produce the hydrogen. One can eliminate that. So when we want to climb that, then obviously you have to do the charge and discharge. Again, we are utilizing the power. So then we have to look at the catalyst also. So there are very continuous this thing. So one can go with the integrating the energy devices, not only the zinc air batteries. So one can go with another other energy devices also to produce the hydrogen, eliminating the external power sources. But again, one has to look at the total cost again.
Correct. So, Professor, the last question is again very generic, where the participant is asking about the unique properties of 3D transition metal complexes that make them attractive as electrocatalysts for energy conversion reactions. So, what are the unique properties of 3D transition metal compounds? So,
unique properties with respect to particular application here?
With respect to applications as electrocatalysts.
This is a very general one. So if I have to go with the energy storage, again, it has a different properties. And if you go with the energy conversion, again, it is a different properties. So only we are looking at that. If you want to develop any catalyst, and even with respect to the catalyst, single catalyst cannot perform a single like. Therefore, you need to go with the composite materials and also integrating with especially the carbon material in order to reduce the overall cost. So for each reaction, if you want to go with that, especially the electrochemical conversion here, in this case, HERR, OER, or the ORR. Here, if you want to go with the ORR, so we go with the adsorption properties, oxygen adsorption. And if I want to go with the hydrogen, so then we have to look at the metal which has a larger the desorption properties and so on. So therefore, this is again, we need to fine tune everything. So we cannot generalize that this is the, we have to look at the criteria of the individual reaction, whether be to the energy conversion or the energy storage devices, and then we have to choose the material.
Thank you so much, Professor Tharamani, for taking so many time again. So Aparna, over to you.
So thank you, Professor Tharamani. This brings us to the end of today's session. We hope that you enjoyed this broadcast very much, and we invite you to view the edited recordings from the past events in the ACS Science Talks library. At the end of the session, you will receive a brief survey. Kindly share your feedback with us so that we can continue to improve and serve you better. On behalf of all of us at ACS, thank you for joining us today. We hope to see you again soon for more ACS Science Talk podcast. Thank you, everyone. Thank you for joining us.
Yeah. Thank you, Aparna. Thank you. Thank you, everyone.